My golly, have you ever been in a steel mill? It is really impressive. Can you imagine what it's like to run experiments in a steel mill? You know, you really must ultimately run experiments with production facilities. If you want to find out how to get the thing to operate at the optimum operating conditions, you best plan some experiments, even though it is a production facility. But of course, experiments here are mightily expensive. And that naturally brings us to our subject, the design of experiments, because our point is to get data as economically and have the data as informative as it can possibly be. We're going to consider today a situation in which there were 4 ways of treating the steel after it had been rolled. And we see the 4 classifications here, the 4 heat treatments. You'll notice this is not a very well-designed experiment in this case. Somebody snafu'd and put more observations on treatment 4 than they did on treatment 1 or 2 or 3. I suspect the plan was to take 6 observations in each one of those treatments, and you know how life is. Somebody snafu'd, but here are the data, and we don't throw data away. So let's do our level best to research and look at this data and see what information it contains. If you eyeball the data, there are no apparent aberrant observations or mavericks. And so let's look at the essential statistics that will encapsulate what's really going on in these observations. And here we have them on the board. There are the 4 treatments, and here are the 4 treatment averages and the numbers of observations in each one of these averages. Here are the 4 estimates of variance and their degrees of freedom. The grand average is 64 with 24 observations, and we've gotten the pooled within estimate of the variance, and it turned out to be a 5.6 with 20 degrees of freedom. Okay, gang, what kind of an experimental design generated these data? And you're all supposed to chorus back a completely randomized experimental design did all of this. In other words, those trials, if they're properly done, were done under complete randomization. I didn't know when I started in that morning whether I was going to do treatment A or treatment B or treatment C or treatment D. I decided which one to run randomly. The appropriate mathematical model for a completely randomized experimental design is the one we see here on the board. And you'll notice that it's a one-way classification, if you will. Each of the observations can be assigned in terms of a mean, a treatment classification, tau sub j, or a treatment effect, tau sub j, and our epsilons. Here's old Mother Nature dumping errors on top of what's really going on and providing us with the observations. And of course, we assume these errors are normally and independently distributed with mean zero and homogeneous variance sigma squared. And we all know, don't we, that in an industrial environment, the size of those epsilons, the magnitude of sigma squared, can be distressingly large. And we're up against a situation where we're trying to learn what in the devil is going on in the presence of a large variance. The usual situation in an industrial concern. Okay, well, here's our design's name and its mathematical model. Let's turn to the board over here and look at the model once again and the parameters which make up that model. We really have to estimate these parameters, and so how would we go about estimating? Well, what are the parameters in our mathematical model? Here's the model. The eta, the grand mean, is a parameter we have to estimate. The tau sub j's, these are the little effects you get for being in one or another of those treatments. And here are the errors, these things that perturb what's going on and give rise to our observations. And these, of course, have the distribution. And there's a parameter in the distribution we're going to have to worry about. We're going to have to get at that sigma squared eventually. Okay, now, how do we estimate the mean eta? Well, the grand average is used to estimate the mean eta. And how do we estimate those little treatment effects? If you had estimates of the tau sub j's, are given by, in this experimental design, are given by the average for that treatment minus the grand average. And that's the appropriate statistic, the one, in a sense, you would have thought of yourself, more than likely, that we use to estimate the treatment effects. And in our example, what did we get for data? What did we get for these estimates? The grand average of 64, and there are the little tau sub j hats. You may remember that the first average was 61, and so what's the estimate of the effect for being in treatment 1? Well, you know, it's 61 minus 64, or the effect, what I estimate, the effect for being in treatment 1 is minus 3. And so it is for treatment 2 and treatment 3 and treatment 4, and you'll all note that those treatment effects sum to 0, as they must. Okay. But now, What I'd like to do is, return to the mathematical model, and I want to take each one of those observations, I want to sort of pull it apart, like you unwind a thread in a sense. Let's take those observations and pick out all their individual components. Okay, well, I've got a surprise for you. I've got a great big box here, which we're going to use. There we go. Isn't that pretty? Have all our observations there once again. See them all? There were the 4 treatment classifications and the 4 observations in treatment 1, and so on down the deck. There they are. And now remember our mathematical model. Our model says that each one of these observations can be resolved in terms of a mean, a treatment effect, and an error. So I'm going to take each one of these observations and I'm going to break it up into its parts. So let's just take one of these observations and see what happens. Let's take this observation right here. That's 67. Okay? And let's break it up. 67 equals. Okay? The grand average. Well, that was right there in the second observation and the second treatment. 64 plus, you see. Now, what was the effect for being in the second treatment? The effect for being in the second treatment was plus 2. All right, now we've got to get that equal sign to work. And to get the equal sign to work, let's go back. Let's see. The 67's equal to 64 plus 2. I need one more to make that equal sign work, and so the residual in this case will come out equal to 1. There they are. Now, gang, I could have done that for any one of those observations. They're all fractured out in the very same fashion. That mathematical model is appropriate for every one of those observations. Now, how does this lock into the analysis of variance? It's very interesting. In some sense, it's almost, I'm always amazed when I do this, that if I take the sum of squares of these observations, it turns out to be 98,644, and we say it has 24 degrees of freedom. That sum of squares also partitions itself in the very same fashion or analogous fashion as those individual observations do. Watch, I'm going to take the sum of squares for the correction factor here. If you take 64 and square it and multiply it up by 24, if you calculate the correction factor, you're going to have 98,304, and we say it costs you a degree of freedom. And now suppose I take the sum of squares of all these particular effects here. It will come out to be equal to 228. And we say it costs us 3 degrees of freedom because only 3 statistics were necessary to get all the elements in that table. And now how about the residual sum of squares? In this instance, the residual sum of squares came out to be 112, and it has 20 degrees of freedom. Why does it have 20 degrees of freedom? Well, there'd be 3 degrees of freedom there. See, they'd have to sum to 0. There'd be 3 there, there'd be 1, 2, 3, 4, 5 there, and 5 there, and 7 there, all of which sums to 20. So there'd be 20 degrees of freedom. But more interesting is the fact that the 98,644, that total sum of squares, has by gum broken itself up into respective components. A piece for the grand mean, a piece for the group deviations, or the grand average, the treatment averages, 228, and finally a residual sum of squares. It fractures out. So about this time, some guy always raises his hand and says, Stu, just a moment. If you take the number 5 and you break it into 2 pieces, 3 and 2, right? 5 is equal to 3 and 2. And then you square the components, 25, sure as the devil doesn't equal 9 plus 4. And you can't argue that. But why in the devil does it seem to work around here? Why those squares seem to work out the way they did? And the reason why they work out is it's the sum of the squares of all these elements that partition out this way. That's the magic of it all. There's a wonderful geometric argument that goes with this. It has to do with the resolution of vectors and so forth. And we'll do that one of these days. That's a great deal of fun. Well, I tell you, let's go back to our analysis of variance table and, put it down in its usual format now. So we have to start out and work all that up. That won't take too much time. Let's see, there's the source sum of squares. And in this case, the corrected sum of squares. You may remember in that instance a moment ago that what the total sum of squares was and the correction factor sum of squares. If you take the difference between them, you get the first entry in the analysis of variance table, which in this instance would be 340. That's the difference between the crude and corrected sum of squares and the crude sum of squares and the correction factor. Then we'd get the treatment sum of squares, and then we'd finally get out the residual sum of squares. And of course, we better pay attention to our degrees of freedom column. Our corrected sum of squares would have 23 degrees of freedom, right? Because there are 24 observations. And the treatment sum of squares would have 3 degrees of freedom because there were 4 treatments, but I only needed 3 of those little effects to get that thing out. And that would leave as a residual the 20 degrees of freedom for the residual sum of squares. Now, gang, before I do another thing to this analysis of variance table, we better talk about the assumptions underlying the analysis of variance table. Now, we could go ahead here and, estimate the variances and use the F ratio, but whoa, right? Before we do that, let's check to be sure that the analysis of variance table, the whole blooming machinery, is in fact appropriate. Okay, so this brings us to the assumptions underlying the analysis of variance. And what are the assumptions? Well, the initial assumption, the most important assumption, I suspect, is that the model is correct. Now, we call our model an additive model because we say the observations can be explained away in things which add together, eta plus the taus plus the epsilons. It's an additive model, and we assume that this model is appropriate. Now, golly, I confess that's a very humble, very empirical, very sort of mundane and ordinary model. It's about the first model you'd postulate for any situation. And we trust it works. We trust it's a reasonable approximation of what's going on. And in many experimental environments is what we seize on initially to see what we can learn. So the first assumption is that the model is additive. Okay, what about the other assumptions? Do you recall when we discussed t, the assumptions underlying the derivation of t, and as far as that goes, the assumptions underlying chi-squared and f? There were 3 important assumptions in that case. And that is that the errors were independent, that they were normally distributed, and that the variance was homogeneous. Those are the essential assumptions underlying the analysis of variance. Those 3 plus the assumption of additivity. Okay, now how in the devil could we check whether or not those assumptions were in a sense being satisfied by our data? And one of the principal clues to whether or not your assumptions are being met rests in the residuals. You must analyze the residuals really before you proceed with any of the other business you can do with an analysis of variance table. Okay, so now let's look at our residuals.